Okay, we'll start in just a minute. All right, we could probably begin. All right, happy Thursday, everybody. Welcome back. As mentioned at a few minutes ago, I haven't had the chance to look over your scratch paper. If you turn that in, I will do so at least before Tuesday next week. I try to get any grading done within a week of submission. So I should have time this weekend to do that, but last couple days it just hasn't been possible. So if you are concerned about that, hold off a little bit. I will get to it, I promise, and you'll see on your grade book. Regardless of whether the score changes or not, you'll see at least that I have looked over your scratch paper. Okay. We open up the modules tab. We are now moving to the test 2 module. So here's our schedule for that. I should update this. This actually should be one day. Oh no, that's right. We're good. What am I saying? I updated this. Oh no, it's not. We're behind. I need to update this. This should say Thursday that we're doing proportions. The lecture notes are here. You should be able to access them. I will tomorrow be able to update these dates so that they are correct. But you should be able to take quiz 1 by the end of class today. That's the only thing due next week. We're obviously not going to get through 2 lessons this week, so you only have 1 quiz next week to think about. Okay, questions on that? Or other questions? Okay. Sounds good. We will start into test 2 material then. We're changing topics a bit now. We have talked a whole lot about unit conversions and how to use those as a problem-solving technique. We're going to start talking about some pre-algebra concepts. Test 2 material is primarily about how to solve certain types of equations using algebra. And today is all about how to solve equations that involve proportions. So that is kind of an overview of what we will talk about now. So first of all, definition. A proportion is an expression that states the equality of 2 ratios or fractions. So anytime you see the word ratio, you can insert fraction if you'd like. So a proportion takes one fraction or one ratio and sets it equal to another fraction or another ratio. Thankfully, these are not, as equations go, these are really not too terrible to solve. We can use a method called cross multiplication to solve any application that involves a proportion. A lot of practical applications do involve proportions like this. Cross multiplication basics is as follows. We are going to multiply the diagonals together. So multiply the numerator of the first fraction by the denominator of the second. And we get 2 times 3, or times 234 in this case. And then multiply the denominator of the first fraction by the numerator of the second, and we can write that as 3 times x. If we do that multiplication, 2 times 234 gives us 468. 3 times x, we could write as 3x. And then if we want to solve this equation, we are going to get x by itself or isolate x. We can do that here by dividing both sides of the equation by that value that x is being multiplied by. So undoing that multiplication of 3 by dividing by 3. And 468 divided by 3 gives us 156. So x in this case gives us 156. Okay. Couple of things that should be mentioned here. We have used x every now and then to represent an unknown quantity. Any type of variable or letter that can represent a variety of quantities, just depending on the context. Any type of variable can be used to represent an unknown quantity. Represents an unknown quantity, or a quantity that we would like to be able to find the value of. We don't know the value as of yet, but we know where that variable exists in the problem. If we want to solve for that variable using the proportion or cross multiplication, we kind of just walked through the process of how you can do it. The basics of that process are, we want to find the diagonal that has no variable involved. So let's see, there are two diagonals. One is the 2 and the 234, and one is the 3 and the x. This diagonal that has no variables involved is 2 and 234. We're going to multiply those two values. Multiply values in diagonal without the variable. Most of the problems that we are going to encounter in this lesson have such a diagonal without a variable. So that would be 2 times 234. We then have one number or non-variable quantity remaining, that's the 3. We can then divide this product, 2 times 234, by the remaining non-variable 3. Then divide by remaining constant. Which in this case is 3, as mentioned. This will be equal to x. And this we can put into our calculator. Two times 234 divided by 3 gives us 156, as mentioned. Oops, that didn't work. Sometimes I will use that set of basic steps. Sometimes I will set it up using cross multiplication. Doesn't really matter to me which you use. If you're an equations person, then you might prefer this middle setup. If you just want a quick go-to, want to be able to plug something into your calculator, then you can use the ladder setup. Both should give you the same answer. Okay. And we're gonna do several practice problems. But before I go to that, do you have any questions for me? We're gonna use this setup to solve some a variety of word problems. So knowing how to solve a proportion is half the battle for this particular lesson. Okay. So several proportions here. I'll do the first couple, maybe the first 3, and I'll let you do the remainder. So for number 1, again, you can solve it by cross multiplication, or you can solve it using that basic process that we talked about. I'll do this first one using both methods. So number 1, using cross multiplication. I am going to multiply this diagonal, multiply this diagonal. So we're going to take 3 times 30 is equal to A times 15. 3 times 30 is 90. It's equal to A times 15. And then finally, if I want to solve for A, I want to get A by itself, so I'm going to divide both sides by 15 to undo that multiplication of 15. That's a basic process of algebra. And then what's on the left, the 90 over 15 is what I'm going to put in my calculator. So 90 divided by 15 is equal to 6. So that is my value for A. This is equal to 6. So A is equal to 6. That's how to do it using cross multiplication. Let's do it using that shorter method, that basic setup. And that's not the technical term for this. That's just what I'm calling it here. I am going to find the diagonal that has all numbers. I'm going to multiply those two numbers together, 3 times 30. And then I can note that the remaining quantity, 15, is what I'm going to divide by. This I can just put into my calculator. 3 times 30 divided by 15. 3 times 30 divided by 15 gives me 6. So same answer regardless of how we do it. Kind of nice sometimes to have 2 different methods. Okay. Let's do number 2. Same idea, just the variable is in a different location. I am going to cross multiply. So I'm going to multiply the diagonals together, set up an equation that has that. 6 times F is equal to 7 times 15. 7 times 15. We multiply that together. We get 105. Can do that in the calculator. And then finally, if we want to solve for F, we can undo that multiplication of F to isolate F by dividing both sides by what F is equal to. I believe 105 divided by 6 is 21, but I could be completely wrong about that. I was very wrong. 17.5. 105 divided by 6. 17.5. So that's what F is equal to. So again, that's one way. Another way to do it would be to note that I want to find the quantity, or excuse me, find the diagonal without a variable. So it is the difference diagonal than the previous problem. So I'm going to take 7 times 15. And then there's one non-variable that remains. That's what I'm going to divide by. Divide by 6. That whole thing gonna go in my calculator. 7 times 15 divided by 6 is equal to, same thing we got before, 17.5. So that is equal to 17.5. Okay. This next one, I'll go ahead and do, but I'm only going to use one method. I think I'll do that basic setup method. That's what I'm probably going to lean towards more in the word problems coming. I'm going to find that diagonal that has all numbers, not a variable. And I'll note that T is equal to 6.6 times 7.5. So I'm going to multiply those two quantities together. And then I have my one constant that remains. I'm going to divide by that constant of 22.5. This can go into my calculator. 6.6 times 7.5 divided by 22.5. So 6.6 times 7.5 divided by 22.5 gives me 2.2, which is not what I got earlier, but seems to be what my calculator got. So that is 2.2. Okay. Yeah, that should be right. That seems right. Any questions on that? All right. Why don't you try this last one? You solve and put your answers in the chat. Okay, good. All right, great. Okay, good. Great. Okay, looks like you all are getting the hang of this. Good. So maybe I'll do this one using cross multiplication. Gonna multiply the diagonals. 2.4 times 0.8 is equal to 3 times m. The 2.4 times 0.8, you should get 1.92 is equal to 3 m. And then we want to divide both sides by 3. 1.9 divided by 3, you should get 0.64, as you all were telling me in the chat. So that should be your m. Any questions on that one? You feel okay about that process? Looks to me like you do. Okay. One thing I will note, I think you all have figured this out, but your quiz for an answer like this will want you to put a leading 0 and not just put 0.64 in the chat. 0.64 is fine, but your quiz will want you to lead any number that does not have a whole part with a 0. So you put 0.64 instead of just 0.64 in your quiz. Okay. All right, so that's half of this, is just knowing how to solve a proportion if you see one, knowing how to find the missing quantity or the value of the variable quantity that will make the equation true. That's the essence of solving an equation, is you're finding what value for the variable makes the equation true. The next part of this lesson is we want to talk about types of proportions found in word problems. The first type that we're going to talk about is a direct proportion. And we are going to use a direct proportion when we're trying to solve a problem for which, let's say we're considering two variables, and as one variable goes up or increases, it causes the other variable to increase as well. So they're increasing at the same time, essentially. Or vice versa, if one variable goes down, if one quantity goes down, it'll cause the other variable or the other quantity in consideration to go down as well. So that's what would be termed a direct proportion. To put it a little more formally, we would say that the numerator of the first ratio corresponds to the numerator of the second ratio. The denominator of the first ratio corresponds to the denominator of the second ratio. So let's think about this in terms of a word problem as an example. A machine produces 280 pieces in 3.5 hours. If the machine works at the same rate, how long does it take to produce 720 pieces? That is what we want to answer. And let's think about like the types of variables that are present. So variables are things that are changing. They're not things that are constant. It looks like we have the number of pieces that the machine produces. So we're given some information about pieces, and that changes. We're also told some information about how long it takes to produce those pieces, the number of hours. We're told a little bit about the rate, but we're told that that rate doesn't change. So it's not what would be termed a variable quantity for this problem. So the rate, we are not going to input directly into our proportion. Okay. So finding the variables is the first step. Once we know what is changing, we're going to find what is called a known relation between the variables. This first sentence says the machine produces 280 pieces in 3.5 hours, so 3.5 hours is our known relation for this problem. This is the known relation. So it's a known relationship between the variables. We know something about both variables for a given situation, a given setup. So X amount of pieces for Y number of hours. That known relation for a direct proportion, we are going to put in the numerator of our fractions, or it'll become the two numerators of our proportion. We're going to have a pieces side of our proportion, and we'll have a number of hours side of our proportion. So I'm going to put one variable on the left-hand side, information about the other variable on the opposite side. The known relation will become the numerators of both fractions. So 280 pieces on the left, 3.5 hours on the right. The second thing we want to find is the remaining quantity that we have not input into our proportion yet, or haven't talked about how it gets input. The 720 pieces, we're asked, how long does it take, or how many hours does it take? That's a question mark. If 720 pieces are made, that 720 pieces will go on the pieces side of my proportion, and it'll go in the denominator because it's not a part of the known relation. If it's not a part of the known relation, it'll go in the denominator. Once we have the setup, we can solve the proportion. Using the same methods we were just using. I'm going to find the diagonal that has has all numbers, so it doesn't have a variable. And then this is my quantity that is not in that diagonal. So to find the number of hours that it takes to produce 720 pieces, I can take 720 times 3.5, product of the diagonal, divide that by the remaining constant, 280, and that will give me my number of hours. So 720 times 3.5 divided by, what did we say, 280? And that will indeed give us 9 hours. Okay. So that is equal to 9. 9 hours for this one. And the nice thing about word problems is that we can typically look back at them and see if this number that we got makes sense. I got 9 for this one, not 9.4. I may have done my calculation incorrectly, but when I multiplied here, I just got 9. So I think it's just 9. But I always appreciate you checking my calculations because they're not always correct. Okay, great. I'm glad that I'm not the only one who got 9. When we look back at the original problem, we're told that in 3.5 hours, the machine produced 280 pieces. So it would make sense that if the machine produced more pieces, it would take more time. This is an example, as mentioned, of a direct proportion that as one quantity goes up, so the number of pieces goes up, the other quantity or the other variable goes up as well. So the number of hours that it takes goes up as well. So we would expect to get a number bigger than 3.5 hours as our solution, which is what we got here. Okay, Questions on that? Okay. Let's do another one. Or two or three. A manufacturing company tests 45 products from its production line and finds that 3 were defective. How many defective items would you expect from a sample of 5,000 products? So as a basic idea for these, we are going to, my pen will work. We're going to set up a proportion. So we're going to take one fraction, make it equal to the other fraction. We want to figure out what are our variables and what is our known relation. We're told in the first sentence that the manufacturing company tests 45 products and finds that 3 are defective. That is an example of our known relation. This is a known relation. It won't always be in that first sentence, but here it is. So it looks like our variables are the number of products produced and the number that were defective. You don't have to do this, but I like to make notes here. Number of products that are produced is going to go on the left, and the number of defective products I'm going to put on the right. Okay. My known relation will go in the numerator. So we have 45 defective or 45 total products and 3 defective products, according to that first sentence, according to our known relation. We're then given some more information. We're asked, how many defective items would you expect from a sample of 5,000 products? Okay. You will get a decimal. Yes, it's true. Given our setup below, if we're given a number of total products, I could find the number of defective. If I'm given the number of defective products, I could find probably how many products were produced to create that sample. But here we're given the number of total products. That'll go in the denominator of the products column. And then I want to find the number of defective products given that. So I'm going to, once I have my setup, I can solve the proportion. So there is my my diagonal that has no variables in it. It doesn't have the unknown. To find the number of defective products in 5,000 products, or the expected number, I should say, I'm going to take 5,000. I'm going to multiply by 3 and then divide by my 45. Okay. So 5,000 times 3 divided by 45. And as mentioned, we do get a decimal here. So 333.33, etc. If my PDF will save, I'll write that down. 0.3 repeating. Since we're talking about products, though, it's probably a good idea to state this as a whole number. So this is the number of expected defective products. So we could probably round down here. So probably 333 expected defective products. Defective products. Because we can't really have a third of a product, probably. Sometimes it just makes sense to round to the nearest whole number. It just depends on the context. Watch the rounding instructions on your quiz. Watch the context of the problems. It will specify how many decimal places to round to, typically, as you have seen. But for something like this, it's probably going to say round to the nearest whole number. Questions on that? All right. Let's see. How many more do I have? Yeah, a couple more. Let's see. Maybe I'll let you do this one. We'll start it and then I'll let you finish it. Medical dosage is typically set up as a direct proportion. It is directly proportional to how much a person weighs. Certain types of medication. I guess it depends. The recommended dosage of a certain drug is 4.5 milligrams per 25 pounds of weight. If a patient weighs 203 pounds, we want to ask the question, how many milligrams of the drug should they be given? Just like the last one, we want to figure out what are our variables? What are the quantities that are changing? What is our known relation? And then how do we use that to set up our proportion? Maybe I'll do the variables first here, and I'll let you do the remainder. It does appear that we are comparing two variables, the number of milligrams of a particular drug given, and the number of pounds that the person weighs, that the patient weighs. Okay. So we're going to set up a proportion with the number of milligrams on one side, number of milligrams of the medicine, and the number of pounds this person weighs on the other side. Great. Yeah. So it looks like you're all already trying this one. I'll give you another couple minutes. If you haven't started working on this, give this one a shot. Setting up the proportion is kind of the second half of this. Okay, good. All right, awesome. These are not too bad, I will agree. As equations go, these are not bad. Okay, great. Yeah, looks like you're getting the hang of it. This is our known proportion. 4.5 milligrams for 25 pounds. So we're going to put the 4.5 on top here. We're going to put 25 pounds on top here. We are asked how many milligrams, asked for the number of milligrams. So the unknown will be in the denominator of the milligram side. We're told that a patient weighs 203 pounds. So that'll go on the pound side. As it appears that you're doing, we're going to multiply the numbers in this diagonal. And then we'll divide by 25. So the number of milligrams needed is 4.5 times 203. And then we'll divide by 25. And as you all are telling me, you should get 36.54 milligrams. Okay. Questions on that?
Yeah, that's not what I'm getting. If I take 4.5 times 203 divided by 25, I'm not getting nothing like that.
Let's try it.
Ooh.
Let's see. 4.5 times 203. Divide that by 25. We should get that. So it might be,
Oh,
yeah.
yeah, I was hitting 2.03.
Okay, yes, that would do it. That would definitely do it. All right, other questions about that one? Okay, great. One kind of nice application of proportions is that of scale factors. If you've seen a CAD drawing or a blueprint or a model, then it's common that you'll have a scale factor written on there. A scale factor gives a ratio between a known distance in a drawing or a model and the corresponding real life distance or real life measurement. So a scale of 1/4 of an inch to 8 inches would tell us that in the drawing or the model, 1/4 of an inch would represent or relate to 8 inches in real life. And if you're given a scale factor, you can treat it as a proportion. We're not going to go through this entire problem just because of our online class setup. Would probably do more of this if we were an in-person class. But let's say we're given this model, this kind of simple drawing, and we're told that the scale factor is 1/8 of an inch is equal to 3 inches. And we want to be able to create the real life model or to find what the real life distances are. So maybe we'll just do the first couple just to see how this works. If we want to find the real life distance for, say, dimension A, which is here, you will not be tested on the models, no, on the scale factors. I'm bringing it in here because it's possible that you have seen these before, you've worked with them. So I think it's kind of a nice application. But I'm just, because of the nature of our class, I'm not going to test you on the scale factors, just the word problem proportions in general. You use them. Okay. Yes. Good to know. This isn't useless information. If I am setting up the scale factor as a proportion, my scale factor I can always think of as my known relation. This is a known relation. So maybe I'll put the scale factor, not the scale factor, the model distance on the left and the real life distance on the right. So scale factor would be 1/8 of an inch. And real life would be 3 inches. So for A, the drawing distance is 3/4 of an inch. So we want to find the real life distance for that. Your calculator can generally handle fractions. We've done a lot. We've done a little bit with fractions. But these types of fractions your calculator can also handle. So I'm going to multiply 3 times 3/4, and then I'm going to divide by 1/8. So A is equal to 3 times 3/4. Divide that by 1/8. So 3 times 3/4. Divide that by 1/8. And we get 18. So 18 inches. So 18 inches. That's another option, yeah. You could convert to decimals if you don't want to deal with the fractions for these. Some of them you can't really convert to decimals, say if you had a third of an inch, but it's not common to work with thirds of inches. It's common to work with fourths or eighths or things that are easy to convert to decimals. So for this particular problem, if you made this in real life, then this dimension here would be 18 inches. So maybe we'll do one more. We'll do B. We're going to use the same scale factor. Use the same scale factor for all of these. So 1/8 of an inch on the left, 3 inches on the right. We don't know the real life distance. We are given the model distance for B right here is 7/8 of an inch. We're going to solve it the same way. Multiply these two together, divide by this. So I get B is equal to 3 times 7/8, which you could convert to decimal notation if you want to, divided by 1/8. So 3 times 7/8 divided by 1/8, and we get 21, looks like 21 inches. Equals 21. So it's kind of a nice application. But we're not sitting in a classroom working with models, so I don't really want to test you on this. I'm more focused on the word problems, but it's helpful to know that you can at least do that setup. Questions on that? Great, good. I'm glad that it helps. Other questions on this one? Okay. I'll leave the rest of those. Let's talk about another type of proportion. An inverse proportion. We talked about a direct proportion happens when if one quantity goes up, as one quantity increases, that causes the other quantity to increase, causes it to go up. An inverse proportion has the opposite property in that if one quantity goes up, if one quantity increases, it'll cause the other quantity to go down. And vice versa. If one quantity decreases, it'll cause the other quantity to increase. We will set these up in a very similar manner. We're going to use proportions, obviously by the name. But instead of one numerator corresponding to the other numerator, it will be the case that one numerator actually corresponds to the denominator of the other fraction. And we'll see how that works. Let's do this by example. A machine can produce, this is a very similar setup to the previous one, so just watch the wording here. One machine can produce 500 pieces in 4.5 hours. So same known relation as our previous problem. One machine can produce 500 pieces in 4.5 hours. We are asked then how many machines would it take to complete the same job in 1.5 hours. So this time we are changing not the number of jobs, but the number of machines. So if machine can produce 500 pieces in 4.5 hours, then it would make sense that if you decrease the number of hours and you have to do the same amount of work, then you would need more machines to complete that job in less time. So as the time goes down, the number of machines goes up. So this is an example of an inverse relation or an inverse proportion. Inverse proportion. If you have an inverse proportion, then that known relation we are going to put in the numerator of the first fraction and the denominator of the second. So we're going to flip-flop them rather than them both quantities from that known relation being in the top or the numerator. We're going to put one in the numerator and one in the denominator. Okay, so this is our known relation. It is still the case that we're making one side of the equal sign represent one of the variables. So this is the machine side still. And then the opposite side represents the other variable. This is the number of hours still on the other side. We're just changing the location of that known relation. The one quantity that we haven't put into our proportion yet is the what if. So how many machines would it take to complete the same job in 1.5 hours? So that goes on the hours side and it'll go in the numerator instead of the denominator. Once we have this set up, we can solve it in the same way that we did those other proportions. So I can take I can find the number of machines by taking that diagonal that has no unknowns. It doesn't have the question mark. And then I can divide by that quantity that is not in the diagonal at 1.5. Okay, 1 times, lost my paper, 4.5 divided by 1.5 is equal to 3. Okay. So that is equal to 3. And now we can again look at what we have and see if our solution makes sense. We are decreasing the number of hours, so it would make sense that the number of machines would increase for a decreased number of hours for the same job. We got a bigger number than 1. So this is probably correct. 3 machines is what it will take to do the same job in 1.5 hours. Okay, questions on that?
How did you know that it was an inverse proportion?
Good question. You will not be told that, I mean, here we're told it is an inverse proportion, but generally you're not going to be told that it's inverse. Generally, what you have to do is look at the variables that you're given and think about whether whether one quantity will increase or decrease as the other one increases. Here I can tell that as the number of, say, hours decreases, then I would need more machines in order to run the same job, probably. So because as one decreases, the other increases, this is an inverse relation. For the previous one, we saw that as one thing increases, the other had to increase as well. So as the number of pounds that a person weighs increases, the number of milligrams of medicine has to increase as well. So that's an example of a direct proportion. So you have to step back and look at the problem that you're given to see how those variables are related, whether when one increases, the other one is going to increase or it's going to decrease. that make sense? Okay, you're welcome.
Yeah, that
that's-
makes sense.
Okay, great. Because that's a great question. Because in your quiz, in your test, you're gonna have to decide, is this an inverse proportion or is this a direct proportion? And you'll set it up depending on that. Let's do another one. On a certain trip, a driver averages 46.2 miles per hour, and it takes him 180 minutes. How long will the trip take if the driver averages 54.7 miles per hour? So I like to start these by first noting, what are my variables? What are the things that are changing? It looks like on this trip, we are given some information about about speed, so miles per hour, and time, 180 minutes. So we have 46.2 miles per hour and then 54.7 miles per hour. So it looks like speed is one of our variables. It's one of the things that we're comparing. So speed in miles per hour. And then time is the other. So it says it takes him 180 minutes. So those are my variables. Once I figure out what my variables are, I have to think about, okay, as one increases, so as the speed increases, as we go from 46.2 miles per hour to 54.7 miles per hour, how will that affect the time? If I'm going faster, and if the trip is the same distance, then it would make sense that the amount of time it would take me to get there is less. So if I'm going faster, it'll take me less time to arrive at a place, in theory. So this is an inverse proportion. Anytime it's an inverse proportion, I'm going to put my speed, my speed here, and then the number of minutes goes in the denominator. So I'm going to put them on opposite sides, one on the numerator and one in the denominator. I'm asked about time. So I'm asked, how long will the trip take? And then I'm given some more information about speed. We're told speed is 54.7 miles per hour. So we have our proportions set up. And yeah, I'm seeing good quantities in the chat. I'm going to multiply those two numbers in the diagonal where there are no variables. So the number of minutes that it will take is 46.2 times 180. And then I'm going to divide by that remaining quantity of 54.7. Let's jump over to my calculator. 46.2 times 180 divided by 54.7 will give us 152. Let's go ahead and round to 2 decimals here. I know we weren't told what to round to, but I'm going to go ahead and round to 2 because time can make sense. A part of a minute does make sense. 152.03. So that's 152.03, and that is in minutes. There we go. And that's a great question, Carson. This is an inverse relation. So whenever your relation is inverse, so whenever as one quantity increases, the other decreases, the known relations will not be right across from each other. The known relations will have the setup where one is in the numerator and the other is in the denominator. So the 180 needs to be in the denominator of the second fraction. So it needs to be across from the 54.7 instead of the 46.2. It's only for a direct proportion that the known relation quantities are right across from each other. Okay. Just looking at our setup here, we expected our time to decrease. So the speed went from 46.2 to the quantity that we're comparing of 54.7 miles per hour. So this is an inverse relation. We would expect the time to be less, which it is. It's fewer minutes than 180. So this probably makes sense. Questions on that? Okay. If you are not sure whether it's a direct proportion or an inverse proportion, then you can attempt to set this up as a direct proportion and just kind of see what happens. So what if I set it up as 46.2, 180, and then put my 54.7 here. And then I did my cross multiplication, multiplied those two, divided by that one. And I would get 180 times 54.7 divided by 46.2. Put that into my calculator and I would get about 213.12. And then still, I have to step back and think about it. If my speed increases, then does it make sense that my time would increase as well? It doesn't. If my speed increases, it would make sense that my time would decrease. So this doesn't logically fit into this setup. If you'd prefer to just go directly to your proportion, not think about, does it go in the numerator? Does it go in the denominator? I don't know. And then think about the logic after the fact, you're welcome to do that. Usually it will be apparent by what your answer is, whether you set it up correctly or not, or whether you should go back and set it back up as an inverse proportion. Questions about that? Okay, a couple more problems. Or three. I think I have three. And this one's kind of a different setup. Two gears, A and B, are in a mesh. Gear A has 25 teeth and revolves at 600 revolutions per minute. We want to determine the revolutions per minute of gear B, which has 75 teeth. Excuse me. All right. So I'm going to start this by figuring out what are my variables. So we've got a couple of gears, and we're told some information about gear A, that it has a certain number of teeth, and it revolves at a certain speed, certain number of revolutions per minute. And then we're told some information about gear B, which also has a certain number of teeth. It has 75 teeth. And we want to determine or figure out the number of revolutions per minute. So those are my variables. That's how I'm going to set up my proportion here. So number of teeth on the left, maybe, and number of RPMs on the right. Okay. I have to figure out if this is a inverse proportion or direct proportion. You can probably guess that it's inverse because it's in the inverse part of this lesson. But let's think about why. The smaller gear has fewer teeth. So if we go from fewer teeth to more teeth, this gear will rotate once. And this gear, it will cause less rotation in this gear. So it will cause, there are more rotations of the longer wheel, the smaller rotations of that small wheel. That small wheel would have to rotate several times to cause the large wheel to rotate once, because the small wheel has a smaller circumference. So it would make sense that the wheel with the smaller teeth, or with the smaller number of teeth, with the fewer teeth, as the number of teeth increases to the bigger wheel, the number of revolutions per minute will go down. So as the number of teeth goes up, the number of revolutions goes down. So this is an inverse relation. Inverse relation. So when it's an inverse relation, I'm going to find my known quantity, and that's for gear A. It has 25 teeth. 25 teeth. And it revolves at 600 RPMs because it's inverse. I'm going to put the 600 in the denominator. The larger gear has 75 teeth. And we want to know in 600 revolutions per minute for the small gear, how do I use that to find the number of revolutions per minute that the larger gear revolves at? Hope that made sense. This one's a little bit more difficult to explain. Once we have the proportions set up, we can solve it. Number of RPMs of the larger gear B are going to take 25 times 600. And then we're going to divide that by 75. Put that in our calculator. So let's see, where are we? 25 times 600 divided by 75, you get 200. Great. 200 RPMs. So by the time the smaller gear has rotated 600 times, the larger gear will only have rotated 200 times. That's what that says. Questions about that one? You all okay with that one? You've probably worked with gears more often than I have. This one I had to think about. All right, sounds good. Let's do a couple more. And yeah, a bicycle is a good model for that. So as you change one gear on a bicycle, then that'll cause you to go faster, slower. All right, let's do these. Let's see, we are given this setup. And we are not told whether these two problems are direct proportion or inverse proportion. I'll do one and I'll have you do the other. I'll do number one. 3 painters are able to paint 500 feet in 42 minutes. If they work at the same pace, how long will it take for them to paint 1,800 square feet? So we're given some information about the number of square feet. Looks like we're given that twice and that changes. So that's one of our variables. And when we're given some information about time, It doesn't look like their pace changes, so it doesn't look like their rate changes. We're not going to use that as a variable. We're going to use the area in square feet as one of our variables, and then the number of minutes that they work at the other variable, or as our other variable. I can't spell bicycle myself, so I understood what you meant. Let's see here. I want to find the known relation. 3 painters are able to paint 500 square feet in 42 minutes. So that is our known relation. Doesn't look like the number of painters change either. It says if they work at the same pace, so we're assuming still 3 painters. It's only our square feet and the amount of time that changes. They were asked how long will it take them to paint 1,800 square feet? Their rate doesn't change, the number of painters doesn't change. It would make sense that if these painters have to paint more area, that the amount of time that it takes them to paint that would increase. So this is an example of a direct proportion. Direct. So that means the known proportion we put in the numerator. We're asked for an amount of time. How long will it take for them to paint 1,800 square feet? To solve this, I'm going to multiply those two, divide by that one. So 1,800 times 42 divided by 500. 1,800 times 42 divided by 500 gives us 151.2. 151.2 minutes. Looks like. Which makes sense. Originally, the 500 square feet took them 42 minutes. So it makes sense that more area would take more minutes. And we did get a larger number, 4 minutes. Okay. All right, in the 3 minutes we have, why don't you try number 2? I'll let you put your answers in the chat. As I see them come in, I will start writing it down below. Okay. Good. Mm-hmm. Okay, great. Uh-huh. Good. So it looks like you figured out this is an inverse proportion. So I'm going to set those, one in the numerator, one in the denominator. We're given the number of workers. We're asked to figure out the number of hours. Good. So we can multiply these two together. Divide by this one. So that means the number of hours it will take 7 workers is 4 times 7.3 divided by 7. which should give you 4.17 hours. All right. Great. Well, that's all, folks. That's all I got. We can call it good, right on time. So let me know if you have questions. Have a good weekend. Thank you, thank you. Enjoy the rest of your Thursday.
You gonna post this video this evening or probably tomorrow?
It'll probably be tomorrow before I'm able to post it, yeah.
Okay, yeah. Sometimes I like to review the whole thing before I do my quiz.
No, that makes sense.
Yeah. It's
Yeah,
something.
it takes a bit to upload, and then I don't always have time in the evening to do it, so.
I understand. I just wanted to make sure it was gonna get posted because reviewing it at a slower pace where I can pause it, it kind of helps me sometimes.
That makes sense. Yep,
Yeah.
I'll post it.
All right. Thank you.
Do we
Mhm.
have a quiz this week, right?
You have a quiz on Tuesday.
On Thursday, okay. On the
Yep.
chapter 7?
The chapter 7 quizzes, technically were due Tuesday this week, but just like the other quizzes, you can always work them after the fact. So if you want to go back and work some of those quizzes, you can.
Okay.
Okay.
All right, thanks.
But this is 8, so 8's the one that's due on Tuesday.
Correct. Yes.
Yeah. Okay. I was trying to print this off while the class was going, and I cannot get this to download on PDF. I don't know why, but it won't go through. It's doing it on a PowerPoint,
Okay.
and it won't print off. I have to do it in landscape mode to get it to print. I tried printing it off in the other way, and all the examples of the equations earlier in this lesson were completely blank. So it must not be compatible for some reason.
Yeah, it might be, if you go to the lecture notes, and if you look at the top,
Yeah, I did that, and
You
I
did that?
clicked on the PDF so I could, because all these lessons we've already
Mhm.
done, I have to download it as a PDF to get it to print
mhm,
and portrait mode. But for some
Mhm.
reason, this one, even though I had the box checked off as a PDF,
mhm,
and you have to scroll down because there's like at the bottom it says download.
yep,
It's
it's not letting you.
well, it'll let me download it as PDF, but all the problems are completely gone. It only shows words and the heading on the
Oh,
side
I
in
see.
blue.
Hmm,
I don't
I
know
see,
why.
yep. It's doing that for me too. Okay, that's good to know, because that's, shouldn't be like that.
Well, I'm
Let
doing
me see what I
everything.
can do.
Yeah, I'm doing everything in a 3-ring notebook, so
Mhm,
I don't want to waste any more paper and ink, so I'm just gonna put
mhm,
this in landscape mode because I tried it a couple different ways and it either cuts half of the page off in portrait mode or it's just blank. It'll give me like the problems in the words, but where like some of them at the beginning were showing like examples in red and green and equals
mhm.
this, when we started it, those are completely blank.
Okay,
I just don't-
I can upload another that is a PDF, if that would be helpful for you.
I'm not a tech whiz, but I can sometimes if I play around with it, I can get it to work. I couldn't get it to work.
Mhm.
Um, sorry, I have a little bit of a cold, but
Oh, no.
um, yeah, I don't know what the deal is.
Yeah, I don't either, quite honestly. I don't know why it's doing that, because it's definitely doing that on my end as well.
I can do it in landscape and just spin my binder sideways. That doesn't bother me at all. I was just wondering if it was something I was doing on my end or if it's just this particular set of lessons. I don't know if the whole we're in like section 2 now, so I don't know if all of them are going to be that way, but I usually have this printed off before the class starts And then
Mhm.
eventually I just, like on the last ones, I was just printing them all off, having them in the book, so when class starts and I'm like just walking in the door,
Mhm.
work, I already had it in a notebook, so I'm ready to just hit Zoom and ready to go, but this
Mhm.
one's just not working right.
Yeah, I see what you mean. I don't know why it's not working right. That is beyond my pay grade, but I
Yeah.
can work around it because I have PowerPoint on my computer. But I am emailing you a copy of it, and then I'll check the remainder just to make sure that it's not doing that for the remainder.
I have PowerPoint too, but when you print out PowerPoint, landscape mode is the only way I can get it to print out without anything missing.
Okay.
Um,
Let's do that. Oop. Oop, don't want two of those. Let's see. Awesome.
I thought it was me.
Nope, doesn't look like it's you. I don't know why it's doing that. But I just sent you the PDF in portrait mode.
So I should be able to just do that right off the email
Yes, you
and
should.
print it off in the
Mhm.
normal mode.
Mm-hmm.
Okay, we'll give it a try.
Okay, sounds good.
Okay. Thank you.
You're welcome.
Have a good evening.
You too. Well, did you have a question? Or are you just still hanging out? All right.